So number 5 says which is an acceptable set of quantum numbers for a 3D electron. Um, 3D is going to be in this region. So this is the D block, I should say. The D block is this part right here. And the 3D is the first part of it. So I guess I may as well highlight a couple of things. The S block is here. And we can move helium over because it just doesn't belong over there for the purposes of electron configurations. So this is the S block. And S starts with 1. So this is 1s, this is 2s, this is 3s, all the way down. The P block is over here. And the P block starts with 2. So you have 2p, and then 3p, and then 4p, and all the way down. We already have the D block here. The D block starts with 3. So that's, let me get rid of this. So the D block is 3D all the way across, and then you have 4D all the way across, and then lastly you have the F block. The F block starts with 4, so you have 4F and 5F in terms of the principal quantum numbers. Now when it comes to L, then that is actually how you determine which one it is. So for the S block, L is equal to 0. And then for the P block, which is purple, the P block, L is equal to 1. And then for the D block, L is equal to 2. And then for the F block, L is equal to 3. So that's one thing that kind of helps. There's a lot more to quantum numbers than this video could cover, so I definitely would say dig back into the quantum number section. Your professor actually has it laid out pretty well. If you have, I think you probably have. So this says which is an acceptable set of quantum numbers for a d electron. How do you think about the n, which is the principal quantum number? First of all, it says 3d, so n is held right here. So since d starts with 3, this means that n is equal to 3 for this whole section here. So it's one of the electrons there. Next one we have L. The reason that we know this is not a great answer, I guess I'll put an X to it here. The reason that we know it's not the second one is because L takes the value of 0 all the way up to 1 minus, or n minus 1. So in the 3D, we have it kind of listed out here so far. In this 3D, we know n clearly equals 3, right? L, what values could L assume? L can only be ever 0, 1, 2, or 3. And the range of the L values is going to go from 0 all the way up to whatever n is minus 1. So if n is equal to 3, based on the fact that it's in that third principal energy level, then L can't be the same as n. That's kind of a big thing here. N can never be equal to L. So that's why the third one is trash, but also the second one is trash. Because even if you thought n was 2, L can't be 2 also. N and L cannot be the same. So that's an important thing to remember. So with that being said, I guess I'll leave that there. We know that that doesn't make any sense. Another thing that really helps. We just said that, use purple to highlight, it doesn't matter, yellow, it doesn't matter at all. We just said that L is equal to 2 for something in the D block. So that kind of is another clue. Just kind of keep those numbers remembered. SPDF 0, 1, 2, 3 for L. So those are L values. So that kind of gives you a clue as well. That's why so far 3 works and 2 works. Can't be 3 and 3, can't be 2 and 2. L and N cannot be the same. And also L clearly can't be greater than N. So we just said that N can't be the same as L, and also N must be less, or N must be, I guess I could just kind of combine this using my math rules. N must be greater than L, basically. So just kind of keep those two things in mind. Moving on with the rest of those, though, then you might be wondering, what about ML? So let's look at the MLs. Just in case you have a question where you have to kind of know a little bit more about it, or you'll probably see coming up. So ML, so M subscript L, that takes a certain range as well. That takes negative L all the way up to positive L. So if L is 2, so L, remember L can't be the same as N, it has to be 1 less or less. But if L is 2, that means that ML takes the range of -2, -1, 0, 1, and 2. And then, of course, MS, which is the one over here, that tells you like whether it's an upspin electron or a downspin electron. Those only can take the values of +1/2 or -1/2. So the only one that makes sense here is the first one. And again, why it makes sense, n equals 3 because it's the 3D. L equals 2 because L can't be the same as n or greater. It has to be less than n. And then ML takes the range of -L. So the maximum value of L, like the maximum absolute value, swing it left to the negative, swing it right to the positive. That's the range of ML. It's just -L to L. And that actually does fit because 1 is in the range of -2 to +2. And then, of course, the spin has to be +½ or -½ That identifies the electron in that suborbital. For number 6, it says how many electrons can be described by the quantum numbers n equals 3 and then ML equals +1. The easiest way that I think you can solve one of these types of problems is to actually sketch out an orbital diagram. So remember, can only hold 2 electrons, and those are just one line or box. So this is going to be 1s, and then you're going to write out 2s, and then you have 2p. So it's going to represent all of those. So yeah, remember, p has 3 orientations, so to speak, x, y, and z. And then you have 3s, 3p, you have 4s, then it drops down to 3, or d, so 1, 2, 3, 4, 5, remember that d can hold up to 10 electrons, 2 per of those orbital thingies, and then you have, see, 2, 4, 2, 3, 4, and you pick up again with 4p, and that's all we need for this to figure out what's going on. As we saw up here, the S has one orientation. It's just a sphere, so it has zeros right there. That's why you represent the S. And then P has L equals 1, so that means the possible ML range for P is -L to +L, as we saw. So we can put a -1, 0, 1, -1, 0, 1. D, remember that for D, L is equal to 2, which means that ML is -2 all the way up to +2. So it's going to be a -2, a -1, a 0, a 1, and a 2. And then again, we have another p orbital, so it's just going to be -1, 0, 1. So this one's a little bit confusing, this question, but once you kind of learn how those orbital diagrams work, definitely review that. It kind of makes some sense as to what this question is asking, because it's really just asking if n is equal to 3. So let's first just find where n is equal to 3. That's here, and here, and here. So if n is equal to 3, but also ML, which is actually in the orange I wrote, but also if ML is equal to +1, how many possible electrons could that describe? So let's find where ML is equal to +1 within the red things I just circled. Well, clearly, S can't have an ML equal to +1 because S has L's only equal to 0, right? So that doesn't make any sense. But what we do have is that, remember, every one of these little orbitals can hold 2. So we can do up, down, up, down, up, down, if we wanted to. Just to remind you, Pauli exclusion principle, Hund's rule, all that stuff. I'm not filling them out according to Hund's rule, but that doesn't matter. I'm just filling them out. So if you wanted to see what Hund's rule looks like, it looks like what I'm doing in 3D. Then go back. That's Hund's rule. But once it's static, it doesn't matter. So up, all the ups, and then all the downs. I don't want to be too hasty, so what I just did with 3D and 4P is I just showed you how Hund's rule works. We might need to get into that a little bit later, but you do all your ups and then go back and do all your downs. That's Hund's rule. It doesn't really apply to 1S because as soon as you do an up, you do a down. But once you do something with P's or D's, Hund's rule applies. Pauli exclusion principle always applies. Pauli exclusion principle says that in every one of these, you can only have a maximum of 2 electrons. And they have to have opposite spins if there are 2 of them in there. Now, let's find where our MLs equals 0. So when our MLs equal +1. Oh, here's one. That qualifies. There's 2 possible electrons right there. So these 2 electrons I just highlighted we have an N is equal to 3 and ML, I guess I'll do it in orange to be consistent, and the ML is equal to 1. That's a possible 2 electrons right there. Let's see if there's anywhere else in those red boxes where we also have a +1, and I see one right here. So we have another 2 possible electrons. Now the spins are going to be up, plus half, minus half, plus half, minus half, but we are only constrained by the fact that it must be n equals 3, but also every time you add a quantum number, you get a little bit more specific. So, but also it says the ML, the orientation, has to be +1. So that actually means we have 1, 2, 3, 4 possible electrons that it fits in. Now, I personally think that the easiest way to tackle questions like this is to actually draw out an orbital diagram and realize how the numbers kind of fit in. For number 7, it says, which of the following statements is false? Let's take a look at the statements one by one. The first statement says an s orbital is found in every main energy level. So I might have to reference this periodic table again. So an s orbital is found in every main energy level. Well, that's true. According to the Aufbau principle, S is the lowest energy level that you could possibly have. Imagine if you're starting. The simplest element, so to speak, is just hydrogen. If even hydrogen exists in the S, so you can't get less than S. So this is a true statement, which means you're not going to select it. The second one, the 3D orbital set can hold a maximum of 10 electrons. Here's how you can verify that. First of all, if you prefer, you can sketch out your orbital diagram. Realize that 3D, 4D, 5D, all the Ds will have 5 lines, but each line can hold 2 electrons. So 5 times 2 is 10. You can also look at the periodic table and just count how wide the D block is. And the D block is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 wide. That just helps you to double verify. By the way, S is 2 wide, so S can only hold 2 max electrons. And the same thing with P. P can only hold a maximum of 6. And you can count, obviously, F holds 14. Even though this periodic table is a little bit wonky because things kind of act weird on the end. This is a really good site, by the way, to kind of study. It's ptable.com. If you click on electrons, it actually shows you electron configuration for stuff. So if you're like, what's the electron configuration and what's the orbital diagram for oxygen, you can clearly see it's 1s2, 2s2, 2p4, and you have, a paired set and some unpaired electrons. You could also see it right there. So this is a really great site. It also shows you the energy levels and all that kind of stuff. Just a good resource to study. So back to here. Where was I? The 3D orbital set can hold a max of 10 electrons. That is true. It is 10 wide, and if you were to count, the 3D is 5 lines. There are no d orbitals when n equals 2. Well, let's look at the periodic table again to verify. When n is equal to 2, you're looking at this section here. Remember, we said that d starts with 3, so of course n can't be 2 if d is equal, or let me say that again. N can't be 2. Right? When n equals 2, there is no d orbital because the periodic table shows that in the second principal quantum level, in the second principal energy level, there is no d block. Also, remember, d starts with 3. So that's a true statement. It's another true statement, another true statement. There are 7 f orbitals in a set. So looking back at the f orbitals, remember f starts with 4. So let's say we do the lowest level f. It would have 1, 2, 3, 4, 5, 6, 7. And the ML set would swing from -3, -2, -1, 0, 1, 2, 3. Because remember, for f, L equals 3. And all that to say, there are 7 orbitals in F. That is true. And remember, each orbital holds a max of 2 electrons. So if it's 2 plus 2 plus 2 plus 2 plus 2 plus 2, that's going to be 14. And that's why the F block is 14 wide. What doesn't make sense, though, is this one. This one says the third energy level has 1 set of F orbitals. So let's take a look at the third energy level. The third energy level has no F orbitals because, remember, F starts with 4. So the reason that this is a false statement is because the third energy level, where n equals 3, doesn't have one set of f orbitals. It actually has none. Because again, f starts with 3. This one we kind of talked about earlier. It says portions of the electromagnetic spectrum. We have 3 waves, A, B, and C. Rank them in order of increasing frequency, so from lowest to highest. Now, it's not hard to tell per se, but there's no number. So what you have to understand is the relationship between the apparent wavelength and the frequency. As we saw, there are a couple equations to consider. E equals h nu. We are not looking at energy. We have another equation that says C equals lambda nu. This one relates wavelength with frequency, and this is the one you want to look at. Now remember, these are inversely proportional. So wavelength is inversely proportional to frequency, which means that when one goes up, the other one goes down. Or when one is large, the other one is small, relatively. So let's kind of look through these. C has a large wavelength. You can say it has a high wavelength. And because it has a high wavelength, it has a low frequency. B has a smaller wavelength. And since we care about frequency, it has a slightly higher frequency than C. Now look at A, and you'll see that A has a super small wavelength compared to the others. Therefore, it must have the highest frequency. And that does match our answers. A has the highest frequency, C has the lowest frequency. If this question had asked about energy, the answers would actually be the same, because remember, frequency is related to energy in this way. Energy and frequency are directly proportional. So if this had asked about energy and frequency will go the same way because they themselves are directly proportional to each other. Question 9, how many of the electron transitions correspond to an absorption of energy? So let's see, if I were to draw out the energy levels, so let's see here, another one. All right, so let's give them some numbers. We have n equals 1, 2, 3, 4, and 5. Now, whenever an electron moves from a lower energy level up to a higher energy level, it's going to absorb energy. So this is going to be an absorption. Okay, good. Sometimes I can't spell that word. And whenever an electron falls in energy level, let's say it falls from 4 down to 1, that's going to be a release of energy. And of course, when an electron falls down and it releases energy, that energy is going to be released as a photon, by the way. So the photon is going to be released. H nu. All right. Now all I got to do is see which one of these are going up. 2 to 4, this is an absorption. 3 to 1, that's a release of energy. 5 to 2 is a release of energy. 3 to 4, that's going up, that's an absorption of energy, and 5 to 4 is a release of energy. So it's asking how many are absorbing energy. There's 2. 2 of them go from a lower energy level up to a higher energy level. Imagine this question being flipped. A really good study tip is to look at a question and then imagine it being flipped. Put yourself in the minds of someone making a test. How could this same idea be flipped around? And think to yourself, well, if I understand that absorbing is going up, then releasing is going down. So think of it that way. This is not, and these are not spaced appropriately. This is not asking you which one is absorbing more or less, because that one you would have to use the Rydberg equation or have some kind of a diagram.